All right, so now we get to talk about the 18 electron rule. And the idea here is very simple. This rule just states that transition metal complexes with 18 electrons tend to be the most stable ones. And so this is directly analogous to the octet rule for main group compounds, which we all are familiar with. And so because now we're talking about number of electrons for transition metal complexes, we have to learn how to count electrons. And so there's several different ways to do this. I'll show you my favorite way. And so the first thing you're going to do is count the number of electrons on the metals. And so the metals contribute the same number of electrons as their group number. So you can look at a periodic table here. Here's scandium, it's in group 3. You're going to count 3 electrons there. There's titanium, it's in group 4. Okay, so you are counting these S electrons. Remember, those do count. Vanadium would be in 5, etc. Then you're going to subtract a certain number of electrons to compensate for the charge, right? So if you're a +1 charge, you're going to subtract an electron. If you're a -2 charge, you're going to add 2 electrons. And then you're going to add in electrons that are contributed by ligands. And for this, please go to the handout on Web Campus that's online. That details very clearly all the different combinations for how to tell how many ligands an electron is going to count. All right, and so, and I'll go over it a little bit how that works here, some of the simpler examples. So let's say you have this complex, a molybdenum hydride, okay, with a phosphine. Could be any phosphine, just saying R groups for the alkyl groups there on the phosphine. There's 4 phosphines. So first, you're going to look at a periodic table, right? And you know that molybdenum is right here in group number 6. So that's 6 electrons. It's neutral, so we don't have to change anything. And now we're going to look for the ligands. Now, the easiest way to figure out if there's a 1 electron ligand is if essentially HX is a stable molecule. And so here we have just an H atom, right? We have 4 H atoms here. So we know that, so X is H in this case, so we know that H2 is a stable molecule. That tells you it's a 1 electron ligand. This is a 2 electron ligand, it's a phosphine. If you add a hydrogen to that, that's not going to be stable, right? Because, you know, that would have too many things bonded to phosphorus, unless it was positively charged, which is not, it's neutral. So this, you know, think about this. This is exactly analogous to ammonia, right? PR3 is exactly analogous to ammonia. And what does that have? That has a lone pair, right? So if you're to draw the Lewis structures of these have lone pairs. And so these are lone pair ligands. They're donating via their lone pair. So these are 2 electron ligands. So we have 4 2 electron ligands. Again, go to the handout to see details about how to assign the number of electrons for different ligands. But we have 4 1 electron ligands to 4 2 electron ligands. That's a total of 12 electrons there, plus the 6 that we originally had for the metal, 18 electrons. Okay? Let's do another example. This is a nickel allyl complex, a diallyl complex. Nickel, look on the periodic table. Here's nickel, it's in group 10, 10 electrons. No charge again, so we don't change anything. And then 2 allyl groups. These are 3 electron ligands. How can you think about allyl groups being 3 electron ligands? Well, there's a double bond. And remember, allyl group is a negative charge there, right? This is going to be nickel 2+, and there's a minus charge on each of these, overall neutral. And so basically you're getting 2 electrons being donated by the double bond, and then you're getting a 3rd electron, okay, due to the negative charge. Why is that? Because again, if you had a hydrogen here, now this would be a neutral molecule, right? That'd be a stable complex. This is a HX type ligand. So this is sort of a lone pair type ligand. It's in the double bond. You can think about that sort of as acting similarly to a lone pair for electron counting purposes, 2 electrons in the bond. And then this minus charge, if you add hydrogen, that's a hydrogen type ligand, so that's 1 electron. So total, we're getting 3 electrons. So we have 2 of these allyl groups, so that gets us with 6. And so 10 plus 6, total of 16 electrons. So this is a stable complex, but you can see it violates the 18 electron rule. This is quite common. There's lots of exceptions to the 18 electron rule. And it all comes down to the energetics of the molecular orbital diagram. We'll learn later on in the course that D8 metals, which this is a D8 metal. Why is this a D8 metal? It was in group 10 electrons, but then it was a +2 oxidation state. So that's 8 electrons, right? Just to be clear, let's do that for this one. Molybdenum was in group 6, right, at 6 electrons. And what's the oxidation state for molybdenum here? We have, this is a neutral by itself, right? PR3, that's a neutral species by itself. And so we have H4, okay? H4, that's, you can think of as an H minus, right? H is a neutral molecule. So in order for this to be neutral overall, you're gonna have to have MO4+. So the formal oxidation state is 4+ for this. So we call this started out with 6 electrons, but it's a 4+, so this is a D2 metal. This, nickel, 10 electrons, group 10, had 2 oxidation states, so we removed 2, has 8 electrons, so this is a D8 metal, okay? We'll learn later on in the course that D8 metals oftentimes are square planar, and that gives rise to 16 electron stable states instead of 18 electrons. So let's keep on going here. This is a cobalt complex. We can do all of this. Let's count atoms first. Go back to our periodic table here where cobalt is 9, group 9, so we have 9 electrons. We have a +1 charge, so we're gonna -1 electron. Gets us down to 8. And then we have these cyclopentadienyl ligands. These turn out to be 5 electron ligands. Unfortunately, there's not too many different types of ligands that are commonly used, so you'll quickly get a feel for these. But again, you can rationalize this. Cyclopentadiene looks like this. This is a dienyl anion, so it's like this, okay? And we have 2 double bonds here, good for 2 electrons each. And then again, we have this negative charge, which is going to be an H-type ligand, so that's 1 electron. Total for 5 electrons, okay? And so we're going to get 18 electrons here, 10, because we have 2 5s, and then the 8 once we're accommodated for the charge. What's the oxidation state? This is a -1 ligand. This is a +3 overall. We have 2 -1 ligands, so it's going to be cobalt 3+, or 3+3. Cobalt 3+, well, is group 9, so this is a D6 metal. So the first set of homework problems for this chapter has you go through, figuring out the number of electrons, figuring out the oxidation state, figuring out the number of d electrons. These are really important skills to hone down when you're talking about learning transition metal chemistry. And so I think we'll stop there and we can do some of these other interesting problems next time.